One of my favourite scientists is Henry Cavendish. Even though he was part of the rich Dukes of Devonshire, that family, and incredibly rich, he went to Cambridge to study natural sciences, or natural philosophy as it's called. But he had a very curious condition in that he could hardly talk to anybody. So when it came to his Viva exam after 3 years of study, he fled Cambridge rather than sit in front of the examiners because he was petrified of them. But he was one of the most brilliant scientists of that 18th century in both chemistry and physics. For chemistry, he's noted because he analysed gases in the air. He discovered there was hydrogen, which is a huge component of the universe. He called it inflammable air. So he put some acids in a container, dropped some metal like zinc into hydrochloric acid, and got the gas to come off. And then to show it was inflammable, you could set light to it, he breathed it in and blew it into a candle. Now, do not do this at home, because it blew up and took all the hairs off his face. He invented the idea of electric potential before everybody else and used to set electric currents through his body to work out the voltage was proportional to current, and he measured the current by the degree of agony he felt with the electrical current. This is not the normal sort of person. He couldn't talk to most people. He couldn't talk to women at all. His housekeeper would get a recipe for something or other, and he'd say, no, lamb tonight, leg of lamb, and leave a note for her. He wouldn't say it, he'd write it. He would dine in the evening with his friends, and he would talk to them, but if he didn't know somebody, and you wanted to ask him a question, apparently you had to go to the Royal Society, and he would be in the room, and you'd address the room this question about physics, and you postulate, and if he felt in the mood, he would reply to the room. He was a very strange man, and yet he's absolutely wonderful. He invented hydrogen. People went up in hydrogen balloons and could see the world from, through that perspective. He did most of the experiments quietly on his own, keeping his notebooks, and it was only after his death and a persuasive campaign by Clerk Maxwell, the famous Maxwell of Maxwell's equations from Cambridge University, that he actually got the notebooks from the estate of the Dukes of Devonshire and discovered after the event that Cavendish had discovered the unit of capacitance, discovered dielectric constants, he discovered Dalton's law of partial pressures, he discovered or written about Coulomb's law, all before these guys had done it, and just left it unpublished in his notebooks. Towards the end of his life, he did a crucial experiment, which is represented by these lead balls. He lived in Clapham Common, which is nowadays a very poor part of London, but there it was quite fashionable. And he built his own place. His library he built somewhere else because he didn't want anybody borrowing his books from his house. Otherwise, he would have to ask the book back, and he didn't want to talk to them. So his library was 4 miles away. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had 2 lead balls, like this, suspended from the ceiling. Only this is not to scale. This is, I mean, lead balls. Now, the real problem is that he wanted to measure the attraction between 2 objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball. So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he could look through, and he put a telescope out there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one, and so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way, and the wire would twist, and as the wire twists, the mirror, which is dangling in there, would twist a little bit, and light which comes in would be reflected off at a slightly different angle, and all he had to do was measure the angle. He then had to move it the other way round. Oh, he didn't move this bit. He moved the lead balls round so that you had an equal and opposite effect on the other side. So instead of having, you'd have that configuration. He had this is a very complicated technical thing for the time. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics, and a lot of chemistry.